All right, in a directed graph, the edges themselves are directed. We think of each edge as like a one-way street. Because they are directed edges, now each edge can be thought of as an ordered pair between two vertices, because now the order in which you write the vertices indicates the direction. We do allow loops in directed graphs. Directed graphs are often abbreviated by calling it a digraph. Each edge, because it is directed, has an initial vertex and a terminal vertex, where it starts, where it ends. We say if AB is an edge going from A to B, we say that A is adjacent to B and B is adjacent from A. So if you see that language used there, that indicates the direction of the edge. And when we talk about degrees of each vertex, because these edges are directed, we're going to indicate whether an edge is going in to a vertex or out from a vertex. So we indicate the out degree of a vertex and the in degree of a vertex. If the out degree of a vertex is 0, meaning edges can only come in and they can't go out, we call that vertex a sink. If the in degree is 0, meaning no edges coming in but only going out, we call that vertex a source. Let's draw this digraph. They've given us a set of vertices and then a set of edges, which we can tell are directed edges because the parentheses indicate that it's an ordered pair and not just a subset. So we have 4 vertices. And now the edges from A to B. Now when I draw a directed edge, I draw it so it kind of bows out a little bit because I want to leave room in case there's an edge going in the other direction. So from A to B, from B to C, from C to C. So that's a loop. From B to D, and from D to B, so I gotta have an edge going the other way. From C to D, and from D to A. So there is that digraph. If we were to focus on a couple of these vertices, like let's say if we look at vertex B, the in degree of B, the edges going in, there are 2 edges going in. I can indicate that, I can see that with the arrow tips. And then there are 2 edges going out. So the in degree is 2, the out degree is also 2. If you look at C, C is interesting because there's a loop there, right? There's an edge from C to itself. The in degree, so that loop is going to contribute 1 to the in degree and the out degree of the vertex C. So the in degree of C is also 2, and the out degree of C is also 2. We allow loops in a digraph. Usually we still don't allow like multiple edges in the same direction, right? So notice like if you look at D and B, right, I have an edge going in each direction, but I wouldn't have like multiple edges from D to B, for example. There are times when it might make sense to allow something like that, and in which case we just call it a directed multigraph. If we label each of the edges, we call it a labeled graph in order to distinguish between the multiple edges from A to B. There's reasons that if you allow multiple edges, it makes sense to label them. We define a directed subgraph analogously to the way we define a subgraph, meaning we have to take some collection of the vertices and edges that were already there. I can't take an edge without also taking the vertices that are adjacent to that edge. I can't change the direction of an edge. Like for example, if I grab the edge from V0 to V1, it has to still, the direction has to be maintained. So here's a directed graph they've given us. We could draw a couple subgraphs. Maybe I'll call this graph they gave us G, G1. Maybe I'll just grab V0, and then these 3 down the middle, V1, V2, V3. And I'll grab these edges from V naught. So here and here and here. And I don't have to grab any other edges if I don't want to, so I'll just stop there. There's a subgraph. Another subgraph, maybe I'll call this one G2. And this time I'll grab the vertex V1, V3, and V4. And some edges. So V4, notice, only has edges coming in, so the only edges I can grab are that edge, and I'll just grab them both. So there's a directed subgraph. Note here in this graph, some bonus information here. V naught doesn't have any edges coming in, right? The in degree is 0. It only has edges going out. So V naught is a source in the graph G. And if you look at V4 here, that only has edges coming in, no edges going out. The out degree is 0. So V4 is a sink. If we have a directed graph, we can construct an undirected graph from that graph, where we just basically we grab each directed edge, except for loops. We don't grab those, but each directed edge just becomes an undirected edge. And we call this graph that results the underlying graph of G. So if this is G, in this one, the same graph as the example above. So I've got this graph G. The underlying graph, which we call G sub S, I'm going to grab all the vertices. And I'm just going to draw these edges without arrows. They're not directed anymore. So that is the underlying graph of G. We say a digraph is connected if its underlying graph is connected. So, for example, here, this graph G is connected because its underlying graph is connected. Right? In this graph, in G super S here, I can get from any vertex to any other vertex. However, there's a stronger sense of connectedness with a digraph. We say that a digraph is strongly connected if for every, and there's a little typo there, no R, for every pair of vertices, there is a directed path from A to B. So in this graph here, G is connected, right? As we already noticed that the underlying graph is connected, but it's not strongly connected because if I start at V4, I cannot get to any other vertex. There's no path from V4 to V naught, right? And in fact, there's no path from V4 to any of the other vertices. So G is connected. Because its underlying graph is connected. G is not strongly connected because there's no directed path from V4 to, I don't know, V1, for example. Or to any other vertex for that matter. But as long as you can find two vertices and say, it can't get from here to here with a directed path, then your graph is not strongly connected. Okay, that takes care of the directed graphs. Our next section that we'll look at are trees, which is a special kind of graph.